Our next speaker is Bastian Bohn from the Universität of Bonn, and he will speak about least squares regression on sparse grid.
Yes, thank you very much, and also thanks to the organizers for giving me the opportunity to talk here. So mainly I want to talk about convergence estimates or error estimates for least squares regression on sparse grids, and we're going to see in a minute what I mean by least squares regression on sparse grid. What I do not mean is that the sample points you draw are aligned on a sparse grid. This setting is also out there, but that's not what I'm going to be concerned with. And also the method I'm going to introduce to you might not be optimal in an approximation theoretic sense. However, it's out there and it's being used very frequently, and that's why I was concerned with estimating the error and maybe also giving estimates for well-postness and stability of this method. And if time permits, we're going to delve into a second part where we're going to see where we might be dealing with problems where the smoothness assumptions are not clear a priori, or where we're dealing with very high dimensional problems. Okay, so very briefly to my motivation, in a very, very sketchy way, what I mean by function regression. So let's say we have a function mapping from the two-dimensional domain indicated here by the square to R, and so this should be the graph of my function. But I'm not really given the function, I'm merely given some sample points, right? So I've some random samples which I throw into my domain, and then I'm given function evaluations. So in the IBC community, you would be talking about standard information here. So I'm given these function values at certain points, and I'm going to say I have small n of them. And then, for example, if you want to approximate now this original function g, which you're only given by these function values, in some reproducing kernel Hilbert space, there is this famous representer theorem telling you that for least squares, for example, or several other cost functions you could think about, the solution is going to be a linear combination of kernel functions which are centered in the data points. So to sketch this here, the red dot would be one data point, and the colors are just the isolines of a Gaussian kernel function. And if you do it, you get a nice reconstruction of your original function g. However, if you do it naively, there are two main problems with this. The one would be that the costs scale cubically or at least quadratically in the number of data points. Of course, there are ways to get around this. However, if you do it naively, that would be one of the problems. And the other one might be, depending on your kernel choice, that your solvers might become unstable for a large number of data points. A natural way to circumvent this would be to introduce some discretization on a grid, like this full grid here indicated by these black dots, and then you take functions with local support on these grids as your basis functions. So here I've taken tensor product of a head function, so piecewise linear, and then you could reconstruct your surface like this. However, all of you will directly see that you get a problem if you do this in high dimensions, because the number of the black points, the number of degrees of freedom you're having is going to explode, and it's going to scale exponentially in a dimension, which I'm going to call m. And you might also see this as the curse of dimensionality, if you will. Then a way to at least get a little bit better with respect to this curse would be to introduce sparse grids here. And so now you're having these anisotropic basis functions on these black dots, again tensor products of head functions, and then you would solve a least squares problem given the blue data points on these basis functions which are centered at the black dots. And this has been done in a couple of papers. There are many more than these. These are probably just the main papers which go in the direction of what I'm analyzing now. However, the question I'm going to be concerned with in my first part is going to be when and why does this actually work? So why should this be a good idea? For example, in this PhD thesis of Dirk Pflüger, he has shown for various examples, also relevant examples from the machine learning community, that this approach might actually in some cases be comparable to state-of-the-art machine learning approaches like support vector machines or Gaussian processes. However, up to now it wasn't perfectly clear why this actually was the case. So if you think about now how to derive error estimates for least squares regression, there might be, I mean, these are all kind of overlapping, but there might be three ways to go for. So there are results, of course, for unregularized regression on splines for full tensor grids, for example, and they're much older than 2002, but in this nice book of Gjörfi, Kohler, and others, there's some results summarized on this. And however, these are for full tensor product grids, so they don't naturally apply for sparse grids. You can't just take these theorems and apply them. Then there is this very nice theory about least squares regression based on approximation spaces or entropy numbers or Kolmogorov n-width in the setting maybe of Cooker and Smale, and also Devore, Temlyakov, and others, where they have been mostly working in the field of getting universal methods, meaning that they should be not really depending on the ansatz you're choosing, they should be universal in the sense that they perform good on various field of applications. And we're going to see in a minute how this setting is going to look like. And then there's least squares function regression on finite dimensional spaces. Also, of course, these works here also work on finite dimensional spaces, but in a very natural and easy setting. This has been looked at by Cohen, Davenport, and Leviathan, and later on many others. So I apologize if I forgot some of them. I just summarized a few of the main contributions to this field. So I'm going to be looking at this problem from two different angles, so to say. One is going to be, I'm going to be deriving error bounds for the sparse grid regression problem with a smoothness regularizer, and this is going to be based mainly on the ideas of Cooker and Smale. And then in the next part, I'm going to be looking at unregularized. What I mean by that is just there's no smoothness regularizer. Of course, it's regularized in the sense that you already discretized your ansatz space by the sparse grid functions, and this is pretty much based on these ideas of Cohen and others. All right, so let's have a more decent look at what I'm talking about. I'm having a domain which I call T, which is in Rm, and for the first part of my talk, this should be some open and bounded domain. So don't think about T as a torus. It doesn't have to be periodic. Usually I'm talking about a non-periodic setting here. Rho is going to be some probability measure on T times R, which I do not know, but I'm given these samples Zn. Ti and xi. So Ti are going to be my latent points and xi are going to be my labels, and I assume they should somehow be drawn IID according to rho. Then I will also need the marginal measure of rho on T, and I will need the conditional measure of rho given T. Whenever I'm going to be talking about LP spaces, I mean the LP space with respect to the marginal measure rho T, okay? And also, I'm always assuming that there is some number R such that rho of T times the interval minus RR is 1. So the image space of your samples can't be arbitrarily large. So almost surely your samples are bounded somehow by R. And now the question is to determine a minimizer in L2, which is called F rho, of this functional E of F, which is nothing else but the integral over the least squares error integrated against the measure rho. But of course, I do not know the measure rho, so we're looking at this empirical quantization error here, which I'm calling EZN, where Zn was my sample set. So this is just the mean squared error, if you will, on the sample set. And now I'm trying to minimize this over I'm going to try to minimize this with respect to F over some set of functions, right? And this set of functions, in my case, is just going to be a scale Vk, where k is going to indicate a level in a way. Later on, it's going to be the dyadic level of sparse grid refinement, and I assume that this is embedded continuously in the continuous functions. And then my search set in the first part is going to be VKB, which is nothing else but a ball of size of radius b in the set Vk. Now, here I have this Vk norm, and I'm completely free to choose this. So usually I choose the same norm for all k. I'm completely free to do this, and this should reflect my smoothness regularizer in the end. So later on, this is going to be a Sobolev norm. So this just means I have functions from my finite dimensional space. I'm going to assume it's a Hilbert space. For the first part, it doesn't matter. It could also be a Banach space, but later on, I'm going to need it to be a Hilbert space. And then I'm looking for functions which, in the Sobolev norm, are going to be having a norm which is now larger than some number b. Now, just for notation, if I'm writing fx, where x is some set of functions, I'm meaning that this is a or the minimizer, depending whether or not it's unique, of e over the set x, and fxcn is going to be a minimizer of ezn over set x. Then I can split my overall arrow, which I'm looking for, which is e evaluated at the function which I can compute. So this would be my least squares minimizer on the set vkb with respect to the sample cn minus e of the function I'm after, which is going to be f rho. And it's quite easy to show that this is nothing else but the squared L2 norm of the difference between the two. So really I'm looking at arrows in L2. And what is common in the field in all of these papers is that you split this into two terms, into the so-called bias, which is an arrow which does not depend on the samples, but merely just on the approximation scale you're having, and then the sampling arrow, which is going to depend on the samples, of course. And usually the way to go here is you take probabilistic Bernstein or Höfting or whatever inequalities, and then you can estimate your sampling arrow, and that's perfectly fine in our setting too, so we're just going to follow this way. And for the bias, or in our case, discretization error, because we're also having to account for having a finite dimensional scale of spaces. So what, for example, Cooker and Smale are doing, they're using real interpolation spaces because they're dealing with functions from reproducing kernel Hilbert spaces. This doesn't apply here because we're having finite dimensional spaces, and there's also ways to work with that, but you have to somehow couple the size of this smoothness constraint you're having in a way, so the size, this radius b, to the discretization scale k. And the question is now how to do this appropriately. Now, since I'm talking about sparse grid regression, let me briefly tell you what I mean by sparse grid regression in my very specific case. Rho t, this marginal measure for sparse grid regression, is going to be the Lebesgue measure in my case. So my samples are drawn according to the Lebesgue measure. And I'm going to be taking this very specific ansatz functions, this very specific basis functions, which is the so-called piecewise linear pre-wavelet basis. You could also take higher order basis, so it doesn't have to be piecewise linear, but for the sake of the argument, let's stick with the piecewise linear basis. This is how it looks like in 1D. It's just a finite linear combination of head functions, and it also has compact support. And this is examples in 2D where you just take tensor product basis functions. And I don't have to tell you how to construct a sparse grid or later on hyperbolic cross with this, but yeah, so this is just the technicalities of constructing these sparse grid kind of ansatz spaces, where you can think of the WLs, if you think about small York methods, just as the delta Ls, which are these hierarchical difference operators. And there's one technicality here, because I'm not really using the L1 norm, but this kind of, kind of toy L1 norm, which is just to assure that the resolution on the boundary, the finest resolution on the boundary, is the same as the finest resolution in the interior. This does not spoil any convergence rates or whatever, however it affects the constants, of course. Okay, then let's come to our first result. So if you take this space scale Vk to be the sparse grid spaces, as I introduced them to you, and if you take the smoothness norm to be the H1 mix norm, what do I mean by this? This is, in my case, the Bessel potential Sobolev norm of dominating mixed smoothness, right? Of order 1 in this case. And then if I know that my true solution stems from this Bessel potential space HS mix, where S is in between 1/2 and 2. So the 2 is here because I'm taking piecewise linear basis functions. If you take higher order basis functions, you can get up to 2 times S, if you will. And then this B is coupled to K like this. So B is going to be 2 to the K times R. The reasoning behind this is that you're looking for, depending on your VK norm, but in our case you're looking for Bernstein inequalities in L2, and then you're pretty much looking at the case, how large do I have to choose B such that my approximation error is just going to be the best approximation error I could achieve in VK. So it's a very naive way to choose B, but for the sake of the argument here, let's stick with this for our first result. Then you can show that this overall error, the squared error, scales like some constant which depends on the dimension times, this is the best approximation error on the sparse grid. This is just pretty much an upper bound for the best approximation error, and the sampling error is pretty much the basis size you're having, which pops up here, divided by the number of samples, and here you have the logarithm of the number of samples again. And this holds with the confidence 1 minus delta, where delta pops up here in the logarithm also. And then if you balance these two terms in a correct way, you come up with a convergence rate of n to the minus 2s over 2s plus 1 times some logarithm to the m. So apart from the logarithm, this is all you could hope for, because this is also what you can achieve in the univariate case for piecewise linear splines on a uniform grid, right? Okay, this is not optimal. Actually, we made a very crude estimate here, and you can get rid of one logarithm at least in this case, but it doesn't matter much here. So the main message here should be that you achieve the main rate that you would get from univariate regression. And you can do the same thing, for example, also exactly the same techniques for hyperbolic cross regression on with Fourier polynomials. So let's say our ansatz space now is the span of Fourier polynomials living on this step hyperbolic cross, and your smoothness regularizer now is the periodic Bessel potential norm, where here I'm taking Fourier coefficients of our Fourier series rather than really applying the Fourier transform as I did in the non-periodic setting. And then if your solution again is from this HS mix space now of periodic functions, now you can get up to arbitrary high S because we're dealing with Fourier polynomials as a basis, and the coupling of B and K is the same. Then again you get a result that you get a best approximation error on the hyperbolic cross here plus this sampling error term, and if you balance these out you get the same thing as above. Okay, so much for this constraint regression setting. Now let's look at unregularized regression where I do not have a smoothness regularizer. So pretty much I'm just minimizing this mean squared error, right? Now if I choose a certain basis, in our case this is this pre-wavelet basis I've shown you before, my basis is going to be called nu1 to nu nk, where nk is going to denote the number of basis functions at level k. Then if I have a linear expansion of my solution as this, so my coefficients are going to be named alpha, then of course I just have to solve this system of linear equations if I want to solve the least squares problem, right? And the question is, when is this actually stable and how is my convergence going to look like? So this is pretty much based, as I said, on those results by Cohen and others, where they did this whole analysis for orthonormal basis. And pretty much all that I've done here is extend this to also non-orthonormal basis. So for non-orthonormal basis, of course, we have to have a look at this mass matrix, which is just a matrix of L2 products of your basis functions you're having. And we're going to be looking at eigenvalues of this matrix. So there is this, unfortunately, I see that I forgot to define this appropriately. So there is this function S of mu1 to nu nk, which is going to be the L infinity norm of the so-called Christoffel function, which is this thing. So it's the right. Yeah, this should be nk. Sorry. So you sum over all the basis functions you're having, square them, and then you take in the L infinity norm of this. So you're looking for point evaluations of this such that this thing is maximal. And you might also have seen this in Clayton Webster's talk on Tuesday, because I think he also uses these for his compressed sensing results. So if this thing is actually bounded by some term, the main argument is here if this is bounded by n over log n. And because we're not dealing with orthonormal basis systems, also here the eigenvalues of your mass matrix pop up. Then you can show that with very high probability your solution is unique, so you can solve the least squares problem, and it's actually bounded by this. Which just means, if you, of course, take an L2 Ries basis, they shouldn't behave differently than this orthonormal basis up to constant. Then a scaling like n log n is sufficient for well-postness and stability. And if you apply this now to the sparse grid setting with this piecewise linear pre-wavelet basis, you get that with high probability our problem is well posed if the number of basis functions you're having is smaller than a constant, which you can compute explicitly, times n over log n. And this constant depends on the minimal eigenvalue of your mass matrix, which is bounded from below because we're having a Ries frame here. So this piecewise linear pre-wavelet basis actually forms a Ries frame. And then you're having these constants down here in the denominator. So now let's look at a very specific regression problem, namely function regression. So instead of having arbitrary labels xi, now I'm really having my true solution f rho, which is evaluated at ti. So I'm assuming that f rho is at least in L infinity somehow, plus some epsilon I, where epsilon I is just a centered noise process with finite variance. And I also need this truncation operator, which just truncates my solution pointwise up to this parameter r we had. Then, if you do the analysis, if this well-postness condition holds, you can show that the expected overall error, now taking this truncation of the true solution, behaves like this. So there are some not really constant terms popping up here, but you can actually neglect them, at least for this Ries frame basis. Here you have the best approximation error on your sparse grid popping up as before. Here you're having the number of basis functions divided by n as before up to a logarithm. And here you're having a term which decays quite fast in n, right, in the number of samples. It decays with minus q, where this q was, let me go back, was this parameter in our well-postness condition. So q pretty much determines how much you oversample in terms of how much more samples do you draw compared to the number of basis functions you're having. And now if you plug this into the sparse grid setting, what you get is if you're having a noise process here, so if epsilon I is non-zero, you're not really improving on the results we had before, right? But in the special case that you have a noiseless regression problem, so your epsilon I becomes zero and your variance sigma is zero, then if your oversampling factor is at least 2 times s, where s is the Sobolev smoothness, and if your well-postness condition holds. So you couple the number of degrees of freedom again to n log n, and your well-postness condition needs to hold, then the expected overall error is going to decay like n to the minus 2s times some logarithmic term. So your main rate really improves. So you can get up, for the piecewise linear setting, you get up to n to the minus 4 as your main rate. But only in the case where you do not have noise on your function regression. And So let's have a look at this for a synthetic problem. We take a very smooth function. I just took this function because in some of the other references it popped up as a surrogate function. You take this function and we're looking at a noisy case where we perturb this by some Gaussian noise, and we're looking at the noiseless case where you take direct point evaluations. Then in the noisy case, this would be the convergence rate we could estimate. So we get at least this would be our upper bound for the convergence rate. And we also see this for this example. And in the noiseless case, this would be our upper bound for the convergence rate, the n to the -4 times log n to the 9. And also this, at least approximately, pops up in our result. So in the remaining 10 minutes, let me talk briefly about how to maybe, so these results are nice and they hold if your true solution stems from this mixed Sobolev space. But what happens if your true solution does not stem from such a mixed Sobolev space, and what happens if you might get up to high dimensions where you can't just use these tensor products of basis functions, which you also had in the boundary, because there the number of degrees of freedom you have in the sparse grid I've shown you is at least 2 to the dimension of your domain. And this, of course, does not work for high dimensional problems. Usually what people have been doing is apply some kind of adaptivity to these sparse grids. And so this works well if the solution you're looking for has some kind of structure. And what I mean by some kind of structure is that its main features, let's look at this function down here, which is just a jump function, so it's 0 in the left part of the domain and it's 1 in the right part of the domain. So if you're having a function like this, and if its main feature, namely the jump, aligns parallel to the coordinate axis, then we're fine with doing some kind of spatial adaptivity, because we just have to adapt along one coordinate axis, because our basis functions are just tensor product functions, right? But now, if you take the same function but just rotate it by 45 degrees, you have a problem, because your adaptive algorithm for these kind of basis functions now pretty much has to employ a full grid around a 2D full grid around this jump to resolve it up to the same accuracy that we did here. And the main idea now to improve the regression is, if you're having a function like this here, try to rotate it or to transform it to a function whose main features now align parallel to the coordinate axis. And how to do this is just looking at the ANOVA decomposition of the function. So I assume you've seen this a lot of times. The standard ANOVA decomposition, now my domain for the remainder is going to be the whole Rm, right? So T is going to be the whole Rm, and I assume that my marginal measure is some kind of product measure, and then I do this standard ANOVA decomposition. So this is the standard L2 ANOVA decomposition. Here's just an example function in 2D which does not have two variate terms in the ANOVA decomposition. And the main thing to take away is that with this L2 ANOVA decomposition, the variance of your function can be split into the sum of the variances of the component functions. And the idea is now to transform the true solution, which we do not know, we're just giving samples, but the idea would be to transform the true solution such that its variance just, or the main part of its variance just resides in the lower order ANOVA terms. And this is up to 80%, let's say. This idea goes back to Jens Oettershagen, who has done something like this in his diploma thesis like 8 years ago. And then we took it now and worked it out together with him for a kind of regression problem with some little tweaks in the method, so to say. So for this, we're looking at this so-called generalized mean dimension. We're assuming that we're having some k, which is smaller than m, and we're looking at just a weighted variance, if you will. So we're taking the variances of the component functions and we're weighting them by omega u. And omega u is going to be this very specific weight right here, which is 1 if u is not a subset of the first k coordinates, and it's this term if u is a subset of this. The reason for this is just that this pretty much corresponds to a weighted kind of truncation dimension in the ANOVA sense. And now our idea is we search for some injective map such that this generalized mean dimension of the true solution after we applied this map is going to be small. So we're trying to minimize this over some set of transformations. And instead of minimizing this, because here we would have to compute all the variances, so we're again left with some 2 to the d or 2 to the m kind of problem, you can show that this is equivalent to just maximizing a problem where you just have to deal with the first k coordinates. Then we're making the assumption that really only the first k coordinates matter after the transformation, and we're throwing away all the rest. So we're choosing some injective map now from Rk to Rm. And in our case, we're choosing pretty much the most simple thing you could think about, namely a linear mapping. So our transformation is going to stem from this so-called Stiefel manifold, which is just the matrices in Rm times k, which are orthogonal. Now, as I said, of course, we do not know our true solution, right? We just are given some points, and what we're doing is now we're substituting the true solution by a polynomial surrogate, which we're finding by least squares regression. So we're solving a very easy least squares regression problem on a polynomial space of, for example, total degree of, or if you want to go up to very high dimensions, just take hyperbolic cross polynomials or something like this. But this doesn't have to be a good approximation to the true solution. This just has to reflect which directions of the solution matter, so to say. So in which directions most of the variance takes place. Major advantage of taking these polynomials is that they're invariant under orthogonal transformations, as from this Stiefel manifold, and that you get closed formulas for computing all these integrals that you have to do for computing the variances of the ANOVA terms. And down here, I've written a CG algorithm on this Stiefel manifold. Don't bother with the details. It's just to show you that you just really have to do some kind of linear algebra. And in the end, you can show that this is the complexity of one CG iteration. Now here d pops up, but d in my case is going to be the total degree of the polynomial, not the dimension. So this is usually something like 2 or 3 in our case. So it's polynomial in this, and the whole algorithm then in the very end looks like this. So I've been dealing with a problem which lives on the whole domain, but to apply these sparse grids from before, I somehow have to transform it to some tensor product bounded domain, right? And to do this, if you know the measure according to which your data has been drawn, then you take the cumulative distribution function to do it. If you don't know, you can just scale it linearly or something like that. It really, in our experiments at least, it didn't matter that much. So the main algorithm is you compute the least squares regression problem on this polynomial space, then you determine this Q by this matrix manifold CG algorithm, and then you transform your original data set by applying Q transpose to it and then the cumulative distribution function. And then on this transformed data set, you perform the sparse grid regression. So it looks like this. You're having this kind of manifold here with some noisy data points. These are the red ones. And the orange line is just to indicate that you rotate this now, in a sense, right? And then you take the transformed data points in red and you do the sparse grid regression in this. And this is just a very special way to do the adaptation. I'm going to skip this. It's just telling you how to actually run the adaptive algorithm. And here you see how it performs for a very synthetic example, which is just a ridge function. So here it should perform quite well, because with the rotation you can bring it down to a parallel to the axis. And in red are two different kind of adaptive algorithms without transformation, and in blue you see the normalized root mean squared error for the rotated versions. And here are the grids for the non-rotated version and for the rotated version. And you see that up to certain degrees of freedom which are there because of the noise, you really catch the main structure of the function, which is just one-dimensional. That's the same thing in 5 dimensions. And here's one more realistic kind of problem where we're looking at a parametric PDE which is a 10-dimensional regression problem where we're pretty much truncating a Cohen-Löw expansion of our diffusivity coefficient after 10 terms and then drawing random samples from it and solving the PDE, and our solution is going to be the average of the PDE solution over the Neumann boundary. So in red and orange you see the 2 different kinds of adaptive algorithms without transformation, and in light blue and blue you see with different kind of regularization parameters you see the versions for the rotated one. And actually the best 2 here are actually better than what you would achieve with lasso, for example, or with Gaussian processes. All right, so just to summarize, I've shown you the error bounds for the well-posedness and for the convergence rates of the unregularized and irregularized sparse grid regression, and how to couple the degrees of freedom and the number of samples. And then I've given you synthetic experiments, at least, which show that these upper bounds are actually met, at least in our synthetic experiment. And then I've shown you some ideas to maybe get around the problem that you can't apply this to very high dimensions, or if the smoothness is not as you want it to be in this mixed sense. All right. Thanks very much for your attention.
Yeah, thanks very much for your talk. Questions or comments? Yes.
Certainly a very important assumption in all this your stuff that marginal measure is a Lebesgue measure.
Right.
It is clear that it's kind of related to your assumption on this prior function that is on. But what if you assume that your this f rho, your regression function, belongs to that mixed smoothness class, but not in L2, but in L infinity?
Mm-hmm.
We know that in that case, and probably in your case it will be the same, that then you can get rid of this assumption and do this for more or less arbitrary marginal measure.
You're right, but you still have to account for one more thing, which would be, so in the first case, for the constraint regression, you still, where is it? There it is. You still have to check which kind of Bernstein inequality you will need to couple this radius of the smoothness assumption to the discretization level, because this will depend on the L2 norm with respect to the measure your data has been drawn according to. So you have to come up with an additional kind of Bernstein inequality. But then if you're already having some kind of Bernstein inequality for the L infinity norm, you would be fine here of taking this kind of regularization. For the second part, for this unregularized problem, you also have to get an estimate on the condition number of the mass matrix. And with that, this inner product in the mass matrix, you of course have to also change the measure. So there you still have the problem that maybe, even though you had a respaces before with respect to the Lebesgue measure, which our pre-wavelets have been, you then have to account for the fact that they might not be respaces anymore with respect to the other measure you might have drawn your data according to. So
you can just take these least squares
right
on this orthonormal basis, and in that case, if I remember correctly, that under this kind of assumption about Kolmogorov widths, for instance, in L infinity, then you can do that stuff.
Yeah, I agree. Probably that should work.
Another minor issue, but it's important. I mean, just minor, that I will not go deep in that. Lower bounds. We did not talk about this, but some of these results look very close to the lower bounds. And lower bounds known in some cases in kind of very general situations. So that means probably it makes sense for you to compare.
Yeah, definitely. So I'm pretty sure that in the unregularized case, this will probably also be a lower bound, but we still would have to elaborate on that. Yeah.
Questions? So maybe I missed the point, but so how do you actually realize this rotation that you? So that's I mean the rotation is found by the algorithm. It's not imposed a priori.
Right. So we're having this kind of, so we're trying to minimize this kind of functional here, where which is equivalent to maximizing. One can show that it's equivalent to maximizing this kind of functional. And all that we're doing is pretty much running this CG algorithm on the matrix manifold stepwise to find a maximum for this functional. So here
phi realizes the rotation.
Phi realizes the rotation. So phi is the rotation, f rho is substituted by a polynomial, and because we substituted it by a polynomial, we can actually analytically compute these guys. So we don't have to do this every step in a CG algorithm. But we still have to run a QR decomposition and all this kind of stuff in every CG step. But it boils down to essentially to stepwise looking for phi in this functional by running this CG algorithm.
Okay, there doesn't seem to be further questions, so thanks again for your talk.